Cool, thanks. Also, thanks to the organizers for setting up this exciting conference. As announced, I'm speaking about causal discovery in time series with unobserved confounders, and by the end of this talk, I hope that you have an idea of what this means. To begin, the motivation of my research is, and I think I share that with many of you, to contribute to a better understanding of the complex systems that we call our Earth, which hosts many dynamical systems that give rise to complex time series. As Caroline said, I'm part of a climate informatics group, which tells you something about the approach of this research. In general, I describe climate informatics as using modern tools from fields such as statistics, data science, and machine learning to support climate and Earth system sciences and the very powerful model-driven approaches in these fields. In the climate informatics group at DLR Jena in particular, we focus on the development of methods. We also implement these methods as open source software that is made available via GitHub for application by domain scientists whom we support and also collaborate with in doing so. Moreover, our methods are largely based in the so-called causal inference framework, which is what I'm speaking about next. From a bird's eye point of view, causal inference is about defining such notions as cause and effect in a mathematical framework. This enables then to cast causal questions within this framework and thereby to develop methods that, under certain assumptions, are able to answer such questions from data. Causal discovery, in particular, is the subfield that is concerned with learning cause and effect relationships from observations. Here again, assumptions are needed already because, as we know, correlation is not causation. Also, more general statistical dependencies do not by themselves imply causation. So in drawing this connection, one really needs assumptions. But then, what is causation? And without claiming that this is the right answer that is always applicable, here is the definition that we work with today. Namely, we say that variable x causes variable y if an experiment that changes the value of x, and that really only does that, so it doesn't change anything else, this leads to a change of y. This is clearly modeled after the experimental, and I think one could also call it interventional mode of inferring causation. And it's in fact what underlies the causal inference framework that I'm speaking about, and which in large parts was developed by Judea Pearl, Peter Spiritis, Clark Klima, and Richard Chines, starting in the late 80s. So now we have a rough idea, at least, of what causation means. Then the next question is, how do we represent cause and effect relationships in a model? And this is what so-called structural causal models, in short, SCMs, do. The intuition here is that one has a certain set of random variables, each corresponding to a certain quantity that one can measure, and an SCM then specifies the functional causal relationships between these random variables, by which nature determines the value of the variables from the value of the other variables. Let me give you an example for this, and as a disclaimer, this example is scientifically oversimplified. It is really only meant to illustrate the general concept. In this example, we have three variables: aerosols, clouds, and environmental factors. An SCM over these variables then consists of three so-called structural assignments, one per variable. Now let's have a closer look at the first one, colored red. Now, this determines the value of the clouds variable from the values of the aerosols and environmental factors variable, which we see because they enter as arguments inside the function of the right-hand side. Hence, we call aerosols and environmental factors direct causes of clouds in this model. Moving to the other equations, we see that environmental factors is a direct cause of aerosols, whereas environmental factors is only determined by this eta variable here, and these eta variables correspond to dynamical noise that subsume all the other effects that are not explicitly part of the model. Yeah? Hence, here in this model, environmental factors doesn't have any direct causes. The qualitative information about direct causation is then graphically summarized in the so-called causal graph. This really is what you think it is. So you have one node per variable, and the directed edges between these nodes correspond to direct causation. For the rest of the talk, we will be more working with causal graphs, not so much with SCMs. At this point, now you may wonder what all this fuss is about. So why do we care about causal relationships? And let me give you 3 reasons why. The first is scientific understanding. I would argue that an understanding of how cause and effect work in a certain natural phenomena is an essential part of its scientific understanding. Secondly, robust prediction and forecasting. It is believed that if one sets up a predictive system in a way that is consistent with the underlying causal structure, in the sense of predicting effects from their causes and not the other way around, then this system will be more robust under changing environmental conditions that lead to changes in the data distributions. Thirdly, attribution. Questions like, why did this event happen, or is this due to climate change? These are causal questions, and thus answering them requires causal knowledge. This brings us to the next question, namely how to obtain causal knowledge. And here I see 3 general strategies. The first and classical strategy is experimentation. That means to design an experiment, perform an experiment, and observe outcomes. The second one is by using simulations. In the climate sciences, we are in the fortunate situation to have very powerful models that emulate the real-world system. And at least for some aspects, it's possible to perform an experiment inside that simulation. For example, running a global climate model with a certain scenario of greenhouse gas emissions can be seen as an experiment inside this simulation. The third approach, and the one that my talk is about, is causal discovery, which means, to repeat, to learn cause and effect relationships from observations under appropriate assumptions. So now let me talk about causal discovery a bit more in detail. This is by itself a wide field, so there are several approaches to it. The one that I'm presenting today, the so-called CI-based approach, for conditional independence-based approach, is about learning the causal graph from statistical tests of marginal and conditional independencies in the observations. And to keep things simple, I just say conditional independencies from now on. This is enabled by several assumptions. The first one is that the observations are generated by some structural causal model. This SCM doesn't need to be known. In fact, for our purposes, it is not known, but it needs to be there. Second, the assumption of no accidental independency. Thirdly, an optional assumption that there are no observed confounders. More on points 2 and 3 soon. But before going there, how does this now work in general? The basic idea is that, and that's a fact, that the structure of a causal graph often imprints certain conditional independencies in the observations, and thus has observable implications. The intuition here is that statistical dependencies only derive from the more fundamental concept that are causal relationships, and that by conditioning on certain variables, one can block but also open the flow of information along certain causal pathways. Let me clarify this with an example. Here, X is a direct cause of Y is a direct cause of Z, and X is an indirect cause of Z through Y. For the moment, we ignore time. We thus expect that 3 pairs XY, YZ, and XZ are dependent because of this causal relationship between them. However, if we happen to know the value of Y, then we wouldn't learn more about the value of Z if we additionally learned the value of X. This is because X influences Z only through Y. Thus, we obtain the conditional independence of X and Z given Y. And that's an example of these conditional independencies that are imprinted into the observations. In fact, there's a more general rule behind. This is known as deseparation, which allows to read off all such independencies that are necessarily implied merely by the structured causal graph. And with this, we can come back to the second assumption of no accidental independencies. This simply means that only those independencies that are necessarily implied by the causal graph are present in the data. So for example, here it shouldn't happen that X and Z are independent. Now, a bit more precise, how does this CI-based causal discovery work? The idea is to first perform statistical tests of independencies in the observations, and then by some algorithm, turn these test results into a consistent causal graph. Again, I would like to clarify this with an example. Here, X and Y and Z are dependent, while X and Z are independent. If we then make this optional assumption of no unobserved confounding, we end up with only causal graph, the one that you see here on the right-hand side, where both X and Z cause Y. Where X and Z were dependent, while they are conditionally independent given Y, there are three possible causal graphs. So here, don't worry about the details of these graphs too much. The point to make is that in general, this approach will not be able to distinguish between all possible causal graphs. So it will constrain them, but we can't decide between all in general. This would only be possible if we were able to make experiments or are willing to make stronger assumptions. Lastly, let me come back to this assumption of unobserved confounding, or no unobserved confounding, rather. Here the point is that if one has two variables, X and Y, that are dependent, and one is sure that these variables are all there is, then one can conclude that X causes Y or Y causes X. However, that rarely is the case, right? Because there could be unobserved variables. And this gives a third possibility, namely that of an additional unobserved variable, call it L, that causes both X and Y. Then, without X and Y causing each other, they still are statistically dependent. And this clearly complicates the analysis. And as a side remark, if you look into publications, is often graphically represented as a bidirected edge between the variables. With this, I can come to research of ours on causal discovery for time series. The motivation is that the world is dynamic rather than static. So one has observations in time. We observe time series. So also the causal graph should obtain a time dimension because the variables are resolved in time, as illustrated by blue color on the right-hand side. Moreover, there's the phenomenon of autocorrelation, meaning that variables at a certain time can be influenced by the values at an earlier by blue color. To be self-consistent, I should say that we make an additional assumption, namely that of a stationary causal structure, which means that the links that you see in the causal graph are repetitive in time, as illustrated in the upper right. Okay, so these particularities of time series data introduce additional statistical challenges. Namely, by resolving in time, one quickly runs into problems of high dimensionality. Moreover, autocorrelation leads to statistical tests of independence that can be ill-calibrated and tend to have low detection power. In summary, this results in standard algorithms often yielding bad statistical performance when being applied to time series. Where our contribution comes in, we have developed several causal discovery algorithms specialized for time series that alleviate these statistical problems. These algorithms are available at GitHub, the link down there, and they're called PCMCI, PCMCI Plus, and latent PCMCI, or in short, LPCMCI. They can be seen as different stages of development, with the more recent ones being less restrictive in terms of their assumptions. Personally, I was involved in the development and implementation of the most recent algorithm, latent PCMCI. So let me go into some more detail here. First, the algorithm allows for contemporaneous links, again illustrated by blue color on the right-hand side, which means it allows for causal relationships that act on timescales shorter than the interval between the measurements. Moreover, and importantly, it allows for unobserved confounders. So consider one wouldn't observe variable x2 in this example. Then the parts of the causal graph that are colored gray wouldn't be part of the causal graph anymore, simply because x2 is not observed. However, in nature, it is there, and it does have observable implications, namely, x1 and x3 at time t do not cause each other, but still they will be statistically dependent because of this unobserved confounder, or also hidden common cause, x2 at time t-1. So here again, we are in the situation of having bidirected edges. Very briefly, the basic idea of this algorithm is to increase the power of CI tests by first iteratively learning direct causes and then using them to extend the conditioning sets in subsequent conditional independence tests. As we observe in extensive numerical experiments, our algorithm indeed outperforms the previous state of the art in terms of recall by a large margin for autocorrelated continuous data. You can see this in the plot down here. It's marked by the red rectangle, where without going into too much detail, the green dots are much higher than the magenta dots. So our algorithm has a higher recall. There would be a lot more to tell about this plot, but I think over time, or in time already, so I would stop here. There are references if you want to have a look. And I'm happy to take your questions if there are any, and I thank you for the attention.